Good afternoon, everyone. Welcome for today's webinar on Altair Computational Fluid Dynamics using next generation Altair flight stream. So my name is Amar. I'm from the marketing department, Design Tech. So today's webinar will be taken by Mr. Gaurav Bhatt. Okay, so Gaurav is an CFD engineer having experience of 13 plus years. So just to introduce the tool, this is a GoToWebinar tool, and we will be having a two-way communication in this tool. However, at the end of the session, we will take up all the questions so that Gaurav doesn't loses its flow. Okay, so Gaurav, shall we start with the webinar?
Yes, Amar, we can start. Thank you for the introduction.
Okay,
Uh,
yes.
so thank you all for joining today's session as a part of Design Tech series of webinars we are doing. So myself, Gaurav Bhatt, I'm working in Design Tech from past 3 years, and I have experience of around more than 10, 12 years in starting with the 3D modeling, then structural, and coming to CFD right now. So the tool we are right now you see here flight stream. It's based on panel method, and the flight stream history and connection goes with the US government long back, around 12 13 years back. Flight stream was originally funded under NASA NIA STTR phase 1 and phase 2 activities few years ago. And then when it at that particular time when eVTOL and urban air mobility was pushed by NASA, and the unconventional complex design couldn't be solved with vortex lattice or similar computational methods, considering the RANS model taking more time in the simulation and couldn't be used for the unconventional designs at that time. As we know, runs take more time in the computational, and where we are talking about vortex lattice or the early conceptual designs softwares, they were very fast enough but couldn't capture the whole phenomena. So where we are talking about hours to days of simulations with RANs and couldn't be applied in complex designs processes in the early stage design, to seconds to minutes of the simulation time with flight stream. The last couple of years, Flystream started receiving funding from DoD, U.S. Air Force, where they are much more interested in transonic and supersonic. As we know, panel method by default it is good for inviscid and subsonic kind of simulations, but whereas U.S. Air Force were more into the transonic kind of simulations, where they are ranging and talking about Mach number up to 1.5, and supersonic where they are talking about Mach number 3. So those kind of simulations for CFD, like computational tool, taking less time, quick glance on the flow parameters in the early stage design to fast process the research activities. That something was received from US Air Force at that time. And also a lot of activities are going on with various US universities like MIT, Cranfield University, etc. So they are working on working on the research activities using this tool. And flight stream and research in flight, basically it was acquired last year by Altair. So early stages, it was named as research in flight, and it was listed under NASA small business success story. The software is approved with US Air Force network approved software that allows the aero and defense bodies to use the software flight stream. So coming directly to the technical capabilities of FlightStream, the FlightStream is essentially a panel method flow software. For some of the Chinese who work with aerospace and defense, you may have heard of the phrase and maybe used it in the past, that I'm sure. So before acquiring the tool by Altair, Research in Flight has worked heavily on research and rewrite the panel method formulation to make it much more efficient, able to handle the compressible flow very nicely, have full viscous coupling, and get rid of some of the limitations that were associated with the older panel methods. So this is all done to enable the aircraft design people to be able to make design decisions in the early stage design stages. The key advantage of the flight stream we are talking here, even though it's a computational method, it works directly on the surface mesh. So there is no volume mesh required. So it is not a a meshless method per se, but we are talking about the surface mesh only. So that makes the tool very lightweight. We are talking about seconds to minutes of runtime. You can run it on single workstations and laptops, and you can scale it to HPC, but for the distributed memory parallelization rather than shared memory parallelization for the given simulation. So this was the background on flight stream. So coming to the application by industrial sector, in terms of applications, the flight stream can address starting with aerospace and defense. Here we are talking about aircraft, missiles, ammunition, and even some of the launch vehicle stuff. Altair is developing now, focusing on external aerodynamics and propulsion. Anything you can do for aerospace, you can definitely do for subsea vehicles like submarines, offshore platforms, navy ships, right? And some of the capabilities under development for ship hulls going in the water. That's something it's under development right now. Automotive side, solar cars teams, so they were already using this tool for the annual competitions and all. And elements of the automotive can be solved under the capability like external aerodynamics on ground vehicles, but that is a limited one as of now on automotive sector. Coming to the wind energy side, the flight stream tool is a natural fit. The panel methods are in use of wind energy side for quite some time now, and they still do. And the same thing is applied to hydro turbines as well. Finally, on the turbo machinery side, due to the capability like transonic flow, we can do simulate the compressors, gas turbines, aircraft engines, pumps and propulsors as of now. So our main focus here, right now in aerospace and defense, and many new changes or the upgradation will be happening under aerospace and defense following the marine side and the turbo machinery after that. So that is what the Altair is developing the tool for further use in marine, where it will be able to capture the shippers going into water like that kind of simulations. Turbo machineries will be the next priority. So where fly stream is positions could not be generalized, and so this chart gives a fair idea on the rep panel method placement comparing to the other empirical and computational methods, which aircraft engineers use for the regular runs model. High fidelity tools like LES DNS for the aerodynamic and propulsion information. Here we are looking at the x-axis, the log scale with the required analysis time in seconds on the x-axis here, and the y-axis is the increasing level of physics. Order it vertically, where you can see the conceptual designs requiring runtime in seconds to minutes, preliminary and detailed one where it goes from minutes to hours, and specialty where you can resolve in high level of physics and you don't need as many design iterations. You can go a bit lenient on the runtime goals, but yeah, specialty again we are talking about days of simulations. So there goes the low fidelity tool where we are looking for very very basic things, right? And then we are talking about the high fidelity on the top, where flight stream lies in this band of mid fidelity. And you see the order of the method here, starting with the empirical methods and the lifting line, which requires very just the surface meshes or just empirical formulas to run around. Okay. So if we starting up in the low fidelity, we have this vortex lattice that dominate the bottom left. Then we have Euler codes that require volume mesh, where we are talking about the simulation taking 20 to 25 minutes of time on a good computer. But again, this is under the inviscid regime only. It cannot capture the viscous effects. And then we have the RANS tools, and talking further on the high fidelity tools like LES and DNS on the top right corner that can solve high level of physics, fairly high on the computational time required. So panel methods just lies somewhere here in the middle band, which solves the medium level of physics in seconds to minutes of the simulation time. And flight stream goes way up on the mid fidelity band because it's rewrapped, optimized, with a thorough optimization. We can do much more with flight stream, like viscous stuff, which is not there in the traditional panel method solvers. You can do flow separation, propulsion, integration, etc. And the flash stream tool is optimized, which keeps the memory and runtime less, hence placed to further left on the conceptual design. And you can see the time taken, relative time taken is lesser compared to the regular panel methods also, even to the Euler codes. The main purpose of the flight stream is to bring the CFD like capability in the conceptual and preliminary stage, where we are talking about minutes of runtime, which was missing currently. And what if GPU comes into the capability for which Altair is working on, and that can take to further left on the time taken for the simulation? We are talking about hence we are talking about the time running the simulations on PCs and laptops in a minutes to seconds, and we are further talking about distributed parallelization, where we can again reduce the time taken. For example, 5 minutes of the simulation can be reduced to 1 minute. Those kind of things we are talking here. So the key ideas, starting with the easy access. So full CAD integration is there. You can import IGS formats, HTL file formats, or if you want to add, parasolid formats, regular CAD tools like CATIA, NX. You can import those kind of models from those kind of softwares. Talking about unstructured and structured grids integration, you can plug in the mesh from Hypermesh, Pointwise, ANSA, etc. Although the FlightStream UI has pre-processing tool for the meshing part, but you can definitely use unstructured, structured surface grids from the market leaders. For now, the CPU parallelization only is there into the capability where you can use shared parallelization. If your system has 12 cores, you can run on shared parallelization, and there is a distributed aspect of that where we are talking about reducing the 5 minute running simulation to 1 minute by distributed parallelization. So that's where the software right now is under CPU parallelization only. And now coming to viscous coupled solutions, here viscous coupled solution, for those of you who have worked with panel methods before, the big distinguishing factor is the full boundary layer viscous coupling added, as well as flow separation capability that allows us to do the boundary layers, drag force, stall capture, and stall prediction, stall angle kind of stuff. So those things you can do with the tool. So the fact that we don't have the volume mesh to worry about, you can do propellers, rotors, and all sorts of motion type simulations. We have 7 level of motion types that you can add into the your simulation for the propellers and rotors. Also, the fact that you cannot do compressibility, you can do now the compressibility part really nicely, so you can do higher speed stuff as well. We can do propellers and rotors in steady and unsteady, both the modes. Coming to the movable surfaces, because you have the control surfaces that can be modeled for high lift devices, flats, flaps. So those kind of settings you can do with the movable surfaces. Coming to jets and turbofans, you are not restricted to the projectile flying through the air without the propulsion. You can do inlet and exhaust. You can model missile pylons, exhaust conditions included. So now coming to this fluid structure interactions, a lot of attention, I guess, will come from this for this capability here. Since volume mesh is not into the play, morphing the geometry really comes down to morphing the surface mesh only. You can do static and dynamic modes both for the wind gust analysis. Okay, so those kind of capabilities right now is available with the rewrapped panel method with FlightStream. So aeroacoustics, the acoustics part was integrated into the tool from the NASA Glenn Center acoustic tools for the tonal and broadband noises, primarily restricted to open rotors or the ducted fans as of now. For example, like it could not be applied on the noises coming out of a moving car as of now. But anything which is related to the open rotors, ducted fans, jets and turbofans, those kind of acoustics we can capture, and the this goes to actually NASA Glenn Center, from where the acoustic tools were integrated into the flight stream. Then easy to use, the graphical point and click interfaces are there. It is integrated with script and batch mode, where you can write a code into the Python or maybe the MATLAB codes, and you can do the scripting and batch mode. So coming to key limitations, that's where we say the decoupled energy equation. Although the exceptions are there, you can simulate the boundary layers, propellers, rotors, flow separations. That's why we are talking about the past simulations. We are solving the simulations for transonic kind of simulations for in less than 5 minutes. Where we are talking about unstudy simulations just completed in 20 minutes of time. Again, it depends on whether we are what is the time step we are using, what kind of flow parameter we are trying to capture. If we are talking about a big time step, Flashstream has no issues in running that. But when we are talking about capturing the whole physics from the minute time steps, definitely it would take some more time, but not compared to the rungs model. So no chemically reacting flows as of now, no combustion modeling or chemical reactions as of now for flight stream. So this is where if there is something related to combustion, we cannot apply flight stream as of now. Those things are under development. We are working on it, but as of now, those things are not available. Single phase flow only, like if we are talking about flow in the air or undersea, that is right now possible. Even the ships moving on the on the sea level, where we are talking air separately and the water separately, but there is no multi-phase applications right now. uh, but you can definitely go for the ship kind of simulations as well, if you are talking about just the external aero and capturing the drag forces on lift forces and the pressure forces applied added on the surfaces. So no fully separated shear flows. For the external flow, if we say we can capture with the interpolation schemes, we can capture very nicely the external parameters. But when we are talking about the cabin internal turbulent flows, so those kind of simulations right now it's not separated, not supported by Flightstream. Whereas external flows, you will be able to capture the details very nicely. But internally, if we are talking about, we cannot capture, as there is no volume mesh right now. So that is some few key limitations in the flat stream tool. So as I have shown you the key ideas, starting with easy access. So CAD integration. Now we are talking about the SolidWorks, Autodesk Inventor, or CATIA. Can be we can import the models from there. And if we talk about vehicle sketch pads like Air Force Engineering Sketchpad, or if you are talking about NASA's OpenVSP, you can definitely import the data and details, geometries from these tools. Talking about CFD grids, Altair hypermesh is directly can be used for creation of the mesh, and then you can import the mesh into the tool, including the pointwise and answer for the meshing part. Structural analysis grids, I mean, we can there's a full integrated one-way two-way coupling with the solvers like OptiStruct, Abacus, Nastran. So you can definitely do nicely those coupling of the tools. Along with that, you can also couple the tool with MATLAB also. For example, you are passing on the information from the flat stream to the MATLAB tool, and then there you can do one-way, two-way coupling. That is also possible with this capability. So component cross sections. So for example, you are into the scripting, yeah, where you say you don't have any CAD, you are into a very early stage, and you want to write a code for the geometry. So you can do that with Python or MATLAB, and you can import that component cross section data into the tool, and you can work on the optimization part of external flow. So talking on the flow regimes, so as we know, panel method, It's good for incompressible. Now we are talking about subsonic, where we are capturing the viscous effects very nicely due to the viscous coupling, fully viscous coupling effect. And then here we can capture the boundary layer ingestions and all those kind of simulations. Talking about transonic and supersonic, which comes after a few years back when Air Force, U.S. Air Force has granted the supported on this one. So, and they actually wanted to see something on the transonic and supersonic side. So that's where it was developed for this kind of capabilities. Right now, hypersonic is on the prototyping, and it will be integrated to the flight stream tool in coming versions. So it's also in the pipeline. So up to supersonic, right now we can nicely capture all kind of simulations. So, talking on the flight stream, it has a full integral, three-dimensional integral boundary layers. Okay, you can definitely do laminar transition and stabilities. You can capture nonlinear lift and moment distributions. Those kind of things you can definitely capture. Computes the implicit simulations actually, and uses the surface velocity fields to compute the attachment lines to surface streamlines and compute the boundary layer. You will be able to capture and have a check on boundary layer ingestions on the aircraft, so etc. So those things are into the boundary layer capability. Here we are talking about boundary layer profile is pretty advanced. Here similar log type scale boundary layer type like you expect from runs tools. You can see the nice correlation with various angle of attacks, and we can see the drag in a momentum deficit simulation. Sorry, yeah. So we can see the drag in a momentum deficit simulation similar to a regular CFD. That's where we can go for this AIAA Aviation Forum and look for this particular paper given in the bottom. And later on also you can contact us. We will be giving you this documentation where you can see the nice correlation with the runs tools. And here we are talking about the time taken is just minutes in a minutes. So, this one is something related to Saffron, one of the customer. They have presented a paper on boundary layer ingestions. Grid here looks very close. You can see right here, right? But flight stream works on linear distribution of the vorticity, and that's the way it is able to capture the ingestions. You can see on the nacelles right here. And considering the 20-second of runtime for this kind of simulations for early stage design, uh, so it's really great. I'm looking at the correlation with NASA wind tunnel and flight stream. So that is something we are talking about here. 20-second of simulations and capturing the pressure coefficients values very nicely on this particular area, right? So we are talking about CL max and stall angle predictions. This F-16, fighter jet, where the separation of line contours, post-stall aerodynamic loads and moments are captured very nicely. You can see comparison with wind tunnel results. Here we are talking about Reynolds number of 1.5.33 million, and you can see the flight stream results, which is giving a fair idea on the capability of the tool for the flow separation as well. So we are also talking about the this kind of flaps, right? You can add multi stalls, multi flaps like that. Here in this graph, you can see the angle of attacks varying from 0 to 25, and then CL, the lift coefficients with a regular Euler code, where it's not considering any kind of viscous effects directly going straight line on the top. Whereas we are talking about the flight stream tool with the regular runs comparison, and we can see a very nice correlation considering the time taken is very small for the early stage design. So the fact there is no volume mesh, we are able to capture the many kind of due to the morphing, we can capture the many kind of motion types, around 7 kind of motion types. Hinge moments all can be set up with arbitrary coordinate movement setup in flight stream. You can do set up the side gaps paired with the leading edge, full gap control surfaces. So those kind of things we are talking here. Simulating the control surface motion for trimming, high lift designs, right? So those kind of movable surfaces options we have with this one. So independently validated and published by NASA, they have written one paper on this. You can see they have applied that to eVTOL, in the AIAA conference on eVTOL site by NASA, paper giving an insight on what to do and what not to do when we are talking about the moving options, movable surfaces. This one is, coming to this one where we are talking about the graphs here, you can see the CLCD and CM results coming out of the wind tunnel data. You can see these dotted lines where we are talking about the error associated with the wind tunnel results, and nicely fitting flight stream data in the blue boxes you can see, which is coming under this band of the minimum and maximum error coming out of wind tunnel. Nicely, computing the things, results and parameters in a very less time. Likewise, we are talking about now the Fowler flaps, slabs, and multi-segment systems. You can see this kind of simulations where we are talking about the high wind gusts coming out of another flaps right this here. This is under X57 program by NASA, where they have used it with Fowler flaps for multi-segment systems. You can see the results right here, CL and the angle of attack, as we are increasing the angle of attack from here -4 to 24, and you can see the comparison of the results, how nicely it is being matching with both the conditions where we are talking about the cruise conditions and takeoff condition. So, talking on the ground effects, Hyphon is another tool in coming out of India, and here it's based on finite volume method on unstructured meshes. You can see the comparison of the tool with the flight stream results. So it can capture the ground effects very nicely. Either we are talking about the study or in study modes. Here, the comparison is made with the CL lift coefficients, and you can see the comparison here with a band of angle of attack of 3 degree, uh, or coming to the axis. Likewise, talking on the CD value, drag coefficient, and again the comparison shows very nice correlation with the drag forces also. Okay, so now we are talking on this one, jet propulsion, where nacelles and pylons modeled in a preliminary detail, where we are talking about the kind of simulations we do in wind tunnel can be very easily set up with our tool flight stream. You can see the correlation here. The lift coefficient and angle of attack ranging between 0 to 100, and we can simulate in the early stage designs the aerodynamic impact of the size, shape, positioning. You can quickly do those kind of simulations in the jet propulsion. So this all goes under the X57 program. You not necessarily here when we are talking about just the wind tunnel kind of simulations. Here we are actually talking about the actual, comparison where we are saying inlets and exhaust aero propulsion kind of analysis, propulsion performance computations, right? So this here you see, CL and angle of attack for a kind of X57 program again, this from NASA. The bottom baseline model you see here, which is comparing with Fun3D, where we have added all the kind of profiles like thrust profile, power, RPM. You can see a very nice correlation where we are just talking about the surface mesh, but you will be able to get the full volumetric wake as a Lagrangian way of by automatically. Here, the CL and angle of attack comparison with Fun3D, where Fun3D we are talking about the weeks of simulations, and the comparison here you see from bottom to top. The bottom one is that's bottom one is for with the regular baseline model, and here the second one we are talking about second with the flaps, And the last one we are saying where we are added the propulsion system along with the flaps. So a nice correlation with the lift coefficients, and then we are talking about the comparison with angle of various angle of attacks in a unsteady kind of simulation. It captures the slipstreams, everything very nicely and accurately. So unsteady solver we have, you see here the kind of Euclidean motion. So seven type of motions we have, as we are talking about just the surface mesh only. So the morphing of the mesh is very easy on the surface mesh. We are talking about the custom motions, FSI, gust kind of simulations, and counters added, right? So those kind of simulations you will be able to do. You can see the store separation kind of model right here, where we can add the exhaust kind of systems with on the missiles as well. And you can see those wobbly kind of movements. Generally, this cannot be captured with any kind of France model. Also, you will be able to capture those wobbly kind of motion of the missile. So we are talking about the arbitrary motions. The regular one is definitely there: rotational, translation, acceleration, flapping, morphing. Uh, Full unsteady, mesh simulation option is available. You will be able to capture the wake regions and capturing the throughout the simulations in a minute of time. This kind of simulations we cannot think of with the RANS model in a very fast way. So this is something coming out uh, into the flight stream software, where we are talking about the full volumetric effects included. So hover and transitions, the time domain simulations, so not restricting the things just with the steady state, and then we are talking about the unsteady here. Hover kind of motions also you can do, where we are talking about just a second. Enhanced, relaxed or wake regions we can capture. Full vehicle interactions on. Again, we are talking about we can couple the pressure forces to the other solvers like OptiStruct and get the effect on the movements. So coaxial rotations, like this kind of rotations, we have counter rotating kind of motions. It can capture very easily. And then we are talking about the comparison here. So thrust and power predictions computed nicely with the good correlation of less than 5% of the the comparison. So the data is correlating under 5% of deviation with the experimental data right here. You can see the rear propeller thrust map. So coming to ducted fans, full fidelity ducted propulsor simulations are there, nicely capturing those gaps in between the nacelle, and then we have this one ducted fan. So it will be able to model those stator rotor systems. Uh, and then again, this was a part of NASA study where they were comparing the results with this thrust and propellers power predictions, which were computed very nicely with the good correlation. You can see the graphs there. So custom motions, like we are talking about the pitching, oscillations, flapping, and morphing. So those kind of things we can definitely do with this flight stream solver, which is unimaginable with the RANS kind of simulation softwares, which it is allows for user-defined motions. I mean, any kind of motion you can set up with the custom motions options we have. So I will be showcasing you more on 6 degree of freedom motions, multi-component and full vehicle motion, right? So here we have to specify if you want to specify, for example, external forces like buoyancy forces, or if you want to add gravitational acceleration, those kind of moments you can add with the aerodynamic loads. You can specify the staggered motion initialization, right? And definitely those kind of things are definitely there, where you can do vehicle gust, turbulence response, passenger right quality kind of simulations. So those store separation, when we are talking about here, wobbly kind of motions. So those things we can capture with 6 degree of freedom motions capability. So this kind of motion where we are talking about multi-component and full vehicle, simulation, talking about the roll angle and roll rate, we can get the coefficient of pressure on this kind of motions as well, which again is very complicated and hard to set up in Rand's model. The kind of motion you see here, going to the right and again in the forward direction, something can be captured in the flat stream tool. Talking about the fluid structure interactions, as you remember in the key ideas, we were talking about fluid structure interactions. So initial surface grid can be passed on to the study solver. User-defined structural nodes also can be done. Then we are talking about either you can write and map the results to the MATLAB code. You can either map that to OptiStruct or Nastran, and then pass on that displacements again to the solid body morphing. Just as we know that we are talking about the volume mesh. Uh, there is no volume mesh in the flat stream, just on the surface mesh, and then you just have to move the surface mesh easily, and then again passing on that information to the another tool. So inbuilt in flat stream, we don't have structural kind of capabilities. We cannot do structural simulations, but definitely it can be coupled with the other tools here. So this is a fair idea you can get from here. Either you can map that to uh, Hypermesh or Nastran or MATLAB tools, and we are talking about one-way and two-way coupling. So linking with the gush models in unstudy solver, von Karman spectral density function turbulence models we can couple this with the multi-body 6 degree of freedom motion definitions. It will be linking this kind of motion coming out of the structural results, mapping again to the CFD part, and you can see here a comparison of the wind tunnel and uh, with our Preston tool, and nicely capturing the whole phenomena. So stack motions, we are talking about uh, rotors with cyclic controls, 6 degree of freedom, right? Vitol transitions, etc. Very nicely. Many geometric motions. You can see the kind of motions it can capture. Uh, just first is starting with this one, then after some time it's going vertically with the hover condition, and then it can capture the whole volumetric phenomena as well, that captures automatically with the interpolation schemes inbuilt into the flat stream. Okay, so coming to acoustic part, so then we are here, again as I discussed in the previous slide also. So NASA is under the NASA funded STTR activity. Acoustic part, the credit goes to, of course, the NASA Glenn Center. They have their inbuilt acoustic tools which was added into the flight stream, and there we are talking about the tonal noise components which can be heard from a person, which is having a very small band of notes, whereas we are talking about the broadband noise starting from all kind of frequencies. So this you can see with the experimental capturing of the this one with the SPL. We are talking about the decibels on the y-axis, and left hand side, right hand side, comparing the results with MUP 2 with the flat stream. You can see the kind of correlation we are getting. Definitely, it's commendable compare when we are talking about the acoustic part, getting the results in minute of time, minutes of simulation time. So a comparison, a paper came from Hansen formulation, and this comparison, you can see this blue one with the Hansen formulation. Nicely, it's coming under all kind of frequencies which were captured with the Flashstream tool. This was validated by with the NASA datasets also, and it was able to come under that particular range where it is able to you know uh, be able to correlate with the experimental details and data. Talking about all the kind of harmonics, first harmonic, second and third harmonic with the Hansen and NASA. So that's as I was saying, we have integrated the NASA tools, which is Hansen, and then we are comparing with the NASA BP this one. So all kind of harmonics here are captured and correlated very nicely. You can see with BPF1 and BPF1 with the dotted one. In this case, you can see this correlation going very nicely here. And like talking about the second harmonic with the blue line here, again the capturing of the dotted lines and this straight line capturing very nicely. And the third harmonic also we are capturing very nicely. So acoustic fields when plane is being placed in below vehicle, when we are talking about 5 meter front of vehicle, and then we are saying 8 meter left of the vehicle. So this kind of acoustic pressure plots you will be able to get acoustic fields from the acoustic simulation data. Likewise, if we are talking about the vehicle comparisons with different uh, if we are talking about the vehicle and we go away from the vehicle at maybe 50 meter, 100 meter, and 150 meter, what will be the overall placement of the noises? Either we are talking about tonal or Brahman noises. So this kind of results you will be able to get from the question tool. So finally, coming to the advanced flow visualizations, although we are saying from the start that the tool is based on surface manual method, and that's why it's very fast, right? But again, we are talking about advanced flow visualization where you can generate various data sections around your vehicle to visualize the flow in very detail. I mean, you can have multiple section cuts at different locations. You can generate the volume data also. Okay. You can have multiple probe points at different locations, probe lines on the nacelles, on the throughout the vehicle. You will be able to get the results like the regular CFD tools we have in the market. So it's all purely comes from the post processing needs only. It again takes some time again for doing this kind of visualization. And again, we are not talking about the hours of time. Again, we are talking about the minutes of post processing time. So, so here we come to the end of this overview of Flightstream tool. I believe I have given the good overview of the tool. So if we have any questions, Amar, we can take the questions.
Yes, Gaurav, thank you for the presentation. So we have few questions. So Mr. Pratik Gupta, he has asked few questions. If you see in the questions tab, so he
Okay,
has
just
written some questions. Also, we will unmute Mr. Pratik
okay, just a second. I'm not able to see. Yeah,
at the top. Yes.
yes, yes. Now I can see. Okay, so first thing, Pratik, Mr. Pratik, that you will be having, if you are going for the tool, we will be having a dedicated training sessions for this one. Also, we have, YouTube page where you can see from start to end the kind of if you are talking about the importing of the geometry, and if you are talking about importing the any third party solver mesh file, so those definitely you can add uh, you can have a check on those YouTube details.
So hello
The
Gaurav, this
second
is
one,
Pratik.
yeah,
So regarding the YouTube tutorials, so I
yeah,
actually saw those videos and
okay,
like the videos presented there, they were on like some particular models and they were uh, actually as you mentioned, they were from
yeah,
start to end. The process was mentioned. But as I said, for my particular case, because I'm not trying to work on a flight directly, I'm trying to work on a
Hmm.
module which goes on to flight. And I was facing an issue because maybe it's some complicated surfaces presented there.
Hmm. Oh, so as of now, you have the tool with you. I mean, you have already bought this software. How it is?
So here, yes. So currently, actually, my company, I work in a company
Hmm.
called Tonbo Imaging, and we have the Altair
Okay.
contract, and we have flight stream with us. And I am
Okay.
trying
Great.
to also do like some kind of CFD. I tried actually the other offers as well, like Hypermesh CFD, and this flight stream was mentioned to me. They said that for my use case, this will be better, so I'm trying to get into it.
Okay. 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 That's great to know, Mr. Pratik. So you have few
Gaurav, just
questions on this one. Yeah.
so Pratik,
Yes,
just
sir.
have
Please.
one question, Abhijit here. So you
Yes.
buy directly from Altair or how it is? Well, something when just want to
I'm from a company called Tonbo Imaging in Bangalore, and
yeah.
we make so the equipments which will go on like fighter jets and stuff, you can say.
Okay, okay. But you have taken Altair directly or how it is from through partner or how it is?
I
You are
am not
aware of?
sure because I am the user, you can say. I'm the user and
Okay,
the CF, like CAE expert in this company, but
okay, okay,
I don't know about the sales part of it.
okay, okay. Fine, no problem.
So yeah, Mr. Pratik. So you have few questions I saw, like you are trying to import IGS format, and that's the only option you were able to see there. And after importing the surfaces, they were not properly read by FlightStream and had gaps,
Yes.
right? So maybe we can let's check because this for this we need to connect and sit and have a check on the tool itself. Maybe later on, if possible, we'll have a check internally also with Altair also, whether we can work around with directly with you and support you on this kind of simulations
Okay.
and the
Gaurav,
issues you are
yeah,
facing. Yeah.
that was my question as well. Is there any possible way where I can get assistance on like how to use the tool? Like rather, is there any class that goes around, or either I can like book a session with someone?
So yeah, so generally it happens like if you have some questions and you want a proper training session on this one, that is being given by design tech to design tech clients. Definitely that we do at our part. But again, we need to again check, Mr. Pratik. I mean, whether you can directly contact to either Altair or you can contact to the reseller who has uh, given you this tool. So directly you can ask them for a training session, and they will be definitely giving you that session.
So
If we
Gaurav,
can,
actually I did that. I went through the community, and through the community I asked this question, and I was directed towards that YouTube videos and also to this
Mhm,
seminar saying that you will get most of the information here. So I had actually gotten much more information, but
yeah.
I am still as you can say that my use case is not really streamlined. It is
Mhm.
pretty peculiar, pretty peculiar use case. That's why I would like some
I
extra assistance
totally
if,
understand. Yeah, I
yeah.
totally
So
understand,
extra
Mr. Pratik.
assistance
Yeah.
if you can provide or anywhere I can directly get it, because if going through online and everything, I don't think it is possible directly there. So I think you have my mail or
We,
my contact number.
yes, Mr.
Yeah.
Pratik. We'll come back to
I
you,
don't want to take everyone's time here, so I just want to say that if you are able to
Mr.
help
Pratik.
me in this regard later, please do it.
Yeah, yeah, definitely we'll be doing and supporting you on that,
Yeah. Thank you,
Mr.
Gaurav.
Pratik. Yeah.
So
So
Gaurav, we have next question from Mr. Vidhan Shukla. How we can use
yeah.
this software? Can we download from any website or anything else?
Okay, so this particular tool as of now can be procured from Altair through us. that is the option available directly. I think the student version is there, we need to check. I mean, I'm not sure about that because recently it was acquired by Altair. We are not thorough with the processes right now, whether students and professors can use the tool just to understand the scenarios and how the tool works. We'll get back to you, Vidhan ji, for that
Sure,
one.
sure.
Yeah.
Because
So
many
Vidhan,
of the
if you,
professors, yeah,
yeah,
many
yeah,
of the
sorry, Vidhan,
professors have asked if the software is free for institutes.
I suspect that, but I think with some few capabilities it will be available. But I'm not again sure because, as I'm again saying, Altair has acquired the tool very recently, and uh, we are not sure about whether it is available for free use or not as of now. But with request, I think it can be provided for some time. With the discussion with Altair through us, we can check definitely that.
Gaurav?
Yes, sir.
Yeah, yeah. So for this, specifically, if you want to use this software, so of course we can help you, sir. Vidhan and uh,
Ak-
someone else
I think
also.
Yes, some other professor,
Akshaya, sir.
Akshay Sinha.
Yeah,
Mr.
yeah, yeah.
Akshaya
So
Simha, they are also asking for whether
yes,
professors
yes.
can use in the institute or not.
Right. So FlightStream is recently acquired by Altair. So there is a that comes under enterprise suite. So if you want to explore these tools, so we will more than happy to provide you a temp license and then we can start working along with you.
Yes, yes.
Okay.
So yeah, so definitely, Mr. Akshaya, we can connect and have a check on providing a temporary license for you, and then we can move further with further discussions. In particular, if you are solving something, we'll be supporting you on that also.
Yeah, so Gaurav, Mr. Akshay is asking if it supports Fusion 360 file format.
So Fusion 360, as of now, I think it's not supported, but we'll have a check because most of the things we are after acquiring by Altair, we are continuously adding more things into it. So as of now, Fusion 360 is not supported, but yeah, we can see that something into the upcoming versions.
Okay, so I request all the attendees, if you have any further questions, you can unmute yourself and you can directly ask the question, or else you can type them in the chat window as well.
Sorry, Gaurav, Pratik here again.
Yeah, Mr. Pratik.
I have a question regarding the solver. So the solver
Mhm.
used by FlightStream is AccuSolve or which one?
No. The solver is based on panel method. Okay, and where we are saying talking about the rewrapped panel method with full viscous coupling. So it's not EcoSol. It's the flat stream itself is the solver. The name is the flat stream.
Okay, so I would
So
say that why I'm asking this question is I
mhm.
tried to use HyperMesh CFD first, and in that
Okay.
there is virtual wind tunnel. Am I right? And then virtual wind tunnel,
Which version you are
thus
using, by the way, Mr. Pratik? Which version you are using right now?
2024.1.
2024.1. Okay, so virtual wind tunnel it comes under ultrafluidex solver. So
Yeah,
that is a
and that
common
solver is
interface
only
HyperMesh CFD has. Yeah.
yeah, that solver is only working on Linux, which is not possible
Ah,
currently for my use
right.
case.
Yes. So GPU machines, it requires GPU machine to run on and Linux solver as of now. So UltraFluidX and EcoSol, they both are can be run under HyperMesh CFD2 user interface. Where when we are talking about EcoSol, it is general purpose CFD solver, and UltraFluidX is that is Boltzmann method based. Yeah.
Yes. So flight stream, I
So you.
believe, for
Hmm.
like the use case which I said to you, for this kind of external flow over a complex body, I think it can be solved. I'm just making sure that it is able to like this software will have like the solver working on Windows itself.
Yes. So it has it can be run on Windows as well as on the Linux.
All right. Thank you very much.
Yeah. So I
So
cannot
Gaurav,
see
yes, there
any
are
other
no other
questions.
questions in the questions tab. So we have unmuted all the attendees. So if anyone wants to
So
ask the question, you can ask there. Yes, Gaurav, you are saying something?
No, no. So we'll just wait for another 2 minutes, and if someone has any question, we can definitely come back.
Sure. Also, I would like to inform all the attendees that we will be sharing the this webinar recording to you with every one of you, and maybe post watching that recording again. If you feel to ask any question, you can definitely ask us at that time as well. On the email, you can reply with your questions. So that fine, Gaurav?
Yes, yes, yes.
Excuse me, sir. Along with those PPTs information, you share his contact number also. That would be
Uh,
better.
definitely, we'll be sharing the contact details as well in the email.
Sure. The
Okay.
session was overall
Sure.
good, but still we require a little bit in detail.
Sure, ma'am. We can arrange a separate call for you as well to answer your
Sure,
queries.
sure, sure, sure.
So,
Thank you, sir.
ma'am, which organization are you from?
Sir, I'm from MMSC Belgaum.
Okay, okay, great. So, yeah, definitely we will come back to you.
Okay, thank you, sir.
Yeah, Mr. Umar. Please take a note on that one also. Yeah.
Okay, so Gaurav, I guess there are no further questions. So I thank
Yeah.
you for this wonderful presentation, and I thank all the attendees for attending this session. Okay, thank you, Abhijit sir, for your support as well.
Thank you,
thank
Abhijit
you.
sir,
Thank
and
you,
thank you,
everyone.
Amar.
Thanks, Gaurav. Yeah.
Thank you, all the team,
Yeah.
all the people who have joined today. We are will be waiting for your questions and any kind of further engagements you want to have with Design Tech. Thank you all. Yeah.
Thanks, Gaurav.
Thank you, Amar. Have a good day, everyone.